Well, it's time for us to do some practice with problems involving Cartesian coordinates and really about distance, and also we'll see spheres coming in as well. And practice is important because it's going to help us develop our geometrical intuition. Now you might say, I know 3 dimensions. I've lived there my whole life. But you know what? We're going to start seeing as we go on, maybe I didn't know everything about 3 dimensions. So it's good to have a good underpinning of your knowledge. And that comes with practice and doing as much as you can on your own. So if you're following along with this video, consider making frequent use of that pause button and saying, okay, let me see if I can do this one. How far can I get? And maybe you'll get all the way. Woohoo! And even if you don't, try to get as far as you can. And then when you get stuck, say, how would I get unstuck? Well, let me see what he did. Ah, that's kind of interesting. That's a nice idea. I can use that in the future. What will happen is you'll start to get better. And we want you to get better. In fact, we want you to be the best. That's our goal. And we believe in you. You can do it. So, with that in mind, let's begin. So our first problem. Find the distance from the point with lots of square roots involved, square root of 19, negative square root of 6, and square root of 30 to a couple places. The origin, the x-axis, y-axis, z-axis, the xy plane, the xz plane, and the yz plane. All right, well, let's begin with the origin. Seems reasonable. So what's happening? Well, when we talk about the origin, what that really means is 0, 0, 0. That's the origin. In other words, you haven't moved. See, that's why we call it the origin. It's where you begin if you haven't moved at all. Okay, so we're really going between 0, 0, 0 and to our point, square root of 19, negative square root of 6, and square root 30. All right. Well, so straightforward distance formula, right? So our distance would be the square root of, and then we take square root of 19, subtract square root of 0, and so we'll go ahead and write it all the way out this time. But oftentimes we'll just write square root of 19, and then squared, and then plus, and then minus square root of 6, minus 0, squared, plus square root of 30, minus 0, squared. Now you might be wondering, does it matter which one comes first? In other words, if I'm trying to get from here to there, say, what's the distance between this point and that point? Is it the same as if I said, let me think of this as my first point and that as my second point? The answer is, of course it won't matter. It'll still be the same thing. So we could have done, for instance, 0 minus square root of 19 and 0 minus minus root of 6. It will all still be the same at the end. All right, well, what do we have? Well, we get the square root of, and of course square roots and squares work pretty nicely, 19. Okay, now this next term, I square square root of 6, I get 6. But wait a second, there's a minus there, so do we add or subtract? We add. Be careful, see, because that square also squares the negative. Whenever you square something, the result should be positive. So we should not ever be subtracting something after we squared it. So that would be plus 6, and then similarly on the end, plus 30. Okay, 19 plus 6 makes 25. Add 30 more, and that makes 55. Well, 55 is not a nice number as far as square roots go, so we'll leave it there. Square root of 55. All right, now we'll turn to the next part, part B. Where are we going? We're going to the axes. So how do we do that? Well, the key is we think about, suppose I'm at a point, x, y, z, and I want to say, what's the nearest point on the x-axis? Well, remember, the x-axis, the y and z coordinates always have to be 0. And so I can say, well, I really want to choose the x value which most closely matches to the x value of the point I'm at. So if I want to do the x-axis, what I would do is I would say, look, if I have a point, square root of 19, negative square root of 6, square root of 30, well, then it's going to have something 0, 0 on the end. And what I do here is I say, look, I want to make these two as close as possible. Well, you can't be any closer than being the same. And therefore, we make this square root of 19 as well. So what happens? Well, when we take our distance, we'll get square root of 19 minus square root of 19 is 0. 0 squared. Okay, 0 plus minus root 6 minus 0 is minus root 6. Square that, be 6. Then square root of 30 minus 0 is square root of 30. Square that is 30. So we're sort of skipping here the intermediate steps of like squaring things. Hopefully you can see how that works. All right. So that's the square root of 36, which, hey, that's looking pretty nice. That's 6. Now, once you see the x-axis, the other axes work very similar. So, for instance, the y-axis will be what? Well, we have our point, square root of 19, negative square root of 6, square root of 30. And what we want to do is want to go to something that looks like 0, comma, something, comma, 0. Well, get as close as to negative root 6 as you can. So, negative root 6. That's the nearest point. So, what's our distance? Well, our distance will be the square root of 19 minus 0, square root of 19. Square that, 19. Then the minus root 6 and to minus root 6 is 0. Square that is 0. And root 30 to 0 is root 30. Square that is 30. Okay, 19 plus 0 plus 30, that's the square root of 49, which is 7. All right, that's kind of nice. It turned out to be a nice number. All right. Well, one more axis, right? Okay, so let's try the z-axis. What do we get? Well, similar idea. Okay, hopefully we're figuring this out, right? So square root of 19 minus square root of 6, square root of 30, and then 2, 0, 0, 0, 0, and square root of 30, right? Because I'm on the z-axis, only the z can be a non-zero entry, so I make it as close as I can by making the z coordinates equal. So we get that our distance here, whoops, I forgot to box my answers. It's a good habit to get into, to box your answers. My distance here would be the square root, and square root of 19 minus 0, squared 19, minus root 6 to 0, it's minus root 6 squared becomes 6, and root 30 to root 30 is 0, so 0 squared is 0, which is the square root of 25, whoops, the square root of 25, and that's 5. Ah, nice, cool, 5, 6, and 7. Wow, it's almost like they wanted nice numbers. And I think it's because they wanted nice numbers. But that's just my personal belief. Okay, so that brings us to part C. Okay, the xy plane. Let's start there. So what's true about points in the xy plane? Well, the z has to be 0. But the x and y can be arbitrary. So if I want to make them close to my point, I say, well, let's make the x values match, let's make the y values match, and let's make z to be 0. So what do we end up with? Well, we're going to take our point, square root of 19 minus square root of 6, square root of 30, to the x and the y stay the same, and the z goes to 0. Now, what happens? Well, when you take our distance, something happens pretty nice. The square root of 19 and square root of 19, no change. Minus root 6 minus root 6, no change. Root 30 and 0, well, that's root 30 squared. Makes that 30. So we end up with root 30. And now the other ones are similar. So we're going to go ahead and write the other ones out. And you can probably make a prediction. And so what do you think? Before we do this, what do you think it's going to be? So I'm going to the xz plane. What's the distance? All right, let's find out. So root 19 minus root 6, root 30. And because I'm in the xz plane, the x and the z are going to be matching, and the y goes to 0. And what do we get for our distance? Well, No surprise, there's no change in x, so that contributes to 0. In y, minus root 6 to 0 is minus root 6 squared, is root 6 squared is 6, and no change in the z direction, so we end up with root 6. And that leaves us just one plane, which is the yz plane. By the way, did you get root 6? You may have thought negative root 6. Let's talk about that in just a second. Let's finish up the yz plane. And so we take our point, and we're going to go in the yz plane. The x coordinate has to be 0, but the y and the z, we want them to match, because if they match, you're not making any change. When you make change, you start to accumulate distance, and the distance builds up. So that's why we want things to match. And so we get our distance. Square root of 19 squared is 19, but in the other directions we don't change at all, so we end up with square root of 19. Okay, now, let's box it, and we're done with the problem, but I think there's an important observation to make here. And here's the important observation. If you look at the answers for part C, root 30, root 6, root 19, they look amazingly like our coordinates. Now, that should not be a coincidence, because what do we think of our x, y, and z? So the way we oftentimes think of x, y, and z, so let's start with just x. So we say, oh, that's our distance we move in the x direction. Oftentimes we do that coming in and out. What's another way to think about it? Well, think about as coming in and out is that you're coming from a wall. So the wall is the yz plane. So the x value can also be thought of as how far am I moving away from the yz plane. In the same similar way, if I think of the floor as the xy plane, the z-axis is perpendicular to it. So I can think of my z value as how far I move away from the xy plane. So when I had the xy plane, the amount I move away is I look at my z-coordinate, and then because I'm doing a measurement of distance, if I were negative, I'd make sure it's positive, which is why we didn't have a minus root 6. We got a positive root 6. All right, good. Well, easy stuff, right? Don't worry. We'll do some more problems. There's plenty of fun ahead. All right, so let's do another problem. Okay. Find the center and radius of the following sphere. X squared plus y squared plus z squared plus 13 is equal to 4x minus 6y plus 8z. Now, our first reaction is that really a sphere? How do we know? Well, first off, it's not so clear it's a sphere. I don't want us to trivialize this. But sort of there's a hint that this should be sphere-like. And the hint is we see the x squared, y squared, z squared. They're all same coefficient of 1, all the same sign. And oftentimes when we see things like that, we think, well, this could probably be a sphere. Now, for us to really help answer our questions, we want to put it into a format where it's easy for us to read the answer. So how do we do that? Well, we know where we're going. We want it to look like a sphere. So that says, I want x minus h squared, y minus k squared, z minus l, there we go, squared equals r squared. So what we want to do is transform from the way that it's given, find a way to rewrite it into the way that we can read off our answer. So it's that rewriting that we're after. And for that, we'll do some algebra. So our basic philosophy is to say, well, let's put things together. So for instance, let's put the x's together. Let's put the y's together. Let's put the z's together. And then we'll put the constants together. All right, so we're going to do a little bit of rearranging. So if we do that, so we're going to move things around. So for instance, I can say I'll have the x squared. I'll move the 4x across, so minus 4x plus y squared. And I'll move the 6y across. Now it's a minus 6y to begin with. When it comes across, it will come across as a plus 6y. Because to move it across, you add 6y to both sides. Plus z squared. and I move the 8z across, minus 8z, and I'll move the 13 to the other side. Now, you might be thinking, he's leaving some suspicious gaps there. I am leaving some suspicious gaps, almost as if I intend to do something there. And that's because I intend to do something. What do I want? Well, the thing is, I don't want x squared minus 4x. I want x minus something squared. So I need to find a way to somehow make it a square. It feels a little bit incomplete right now. So, is there a way for us to somehow complete the square? And the answer is, yeah, there is. It's called completing the square, right? Okay, how does that work? Well, the idea says, what would I need to put into this slot so that the first piece were a perfect square? So the rule is, you take the middle term, divide it by 2. Okay, that's not so bad. That'd be negative 2. Square it. Negative 2 squared, 4. So that says if you added 4 here, then, lo and behold, you can see this becomes x minus 2 squared. Woohoo! It's a perfect square, right? Good. Now, we've cheated a little bit, but we're going to undo our cheat. We added 4. So we have to find some way to compensate for that 4. Now, oftentimes there's multiple ways to do it. One way you can do it is immediately subtract 4. So plus 4 minus 4, because then you've added 0. Or another way is to say, look, let me do something equivalent somewhere else so it exactly balances out. So for instance, I added 4 on the left, so I'll add 4 on the right. And therefore, I maintain balance. So, plus 4. Okay, let's go to the next term. Y squared plus 6y. What do we need to add? Well, take 6 divided by 2 is 3. Square that is 9. So I need to add 9. Do it immediately on the right as well, so that we've kept things in balance. Good. So this becomes y plus 3 quantity squared. Z squared minus 8z. Okay, take the middle term, divide by 2. Negative 4, square it. Says add 16. So over here, add 16. Now, this term becomes z minus 4 squared. Okay, good. Now, how about over here? Well, let's just add things up. Negative 13 plus 4 plus 9, well, that all cancels out, and so we're left with 16. Or, if you like, 4 squared. Now we're ready to read off our answer, because it says find the center and radius. So, where's our center? Well, we say the HKL is our center, so H, that's our x-coordinate, would be 2. What's the y-coordinate? Negative 3, right? Because, you see, it should be y minus something, not y plus something. So this is secretly y minus 3. So negative 3, y, our z-coordinate, positive 4, and our radius would be 4. Right? R squared is 4. Good. And there you go. Complete the square. Nice. Good problem. Okay, well, let's try another problem. Okay. Find the minimum distance from a point on the sphere x minus 1 squared plus y squared plus z minus 2 squared equals 4, and a point on the sphere x plus 2 squared plus y minus 5 squared plus z plus 2 squared equals 9. Now we know that these are spheres because they're written in the right format, which is great news for us. So now we say, okay, what do we need to do? Well, we see the word minimum, right? And we think to ourselves, hey, we've been doing calculus for a while. Minimum, optimization, let's do some calculus. Woo! That's actually going to get tricky, though. Because just think about what's happening here. If we think of the picture, well, what do we have? We're in three-dimensional space, so we have a sphere somewhere. We'll say this is one of our spheres. And then we have a sphere somewhere else. Here's another sphere. Now, you might be thinking to yourself, how did you draw them so quickly? Well, one of the things I'm going to tell you many times is I'm not really too worried about precision oftentimes. So for right now, I'm not worried about precision. I'm just worried about intuition. And so for intuition, I just say, draw us two spheres, and let's think about what's going on. Now, the reason why calculus would be hard is because we'd have to somehow find a way to have a minimum where we think of going over all the points over here and all the points over there all at the same time. Oh, that sounds tough. Because it's tough. It's not an easy thing to do. And we don't have the tools to do it. Okay, so now you might think, well, maybe we can't do this problem. And the answer to that is we can if we start thinking about the geometry. So let's focus on the geometry. And one thing to help us is to say, look, don't necessarily start in 3 dimensions. Step back. Think about what's happening in a smaller, simpler setting. This is a great way to go about problem solving. Reduce it to something easier to work with. So in that case, suppose I had 2 circles. So here's one circle, and here's another circle. And I wanted to ask the question, what's the distance between them? Now, here's the sort of the key idea, is the following, is let's look at what happens when we connect the centers. All right, so I've now connected the centers. What's true? Well, what's true is the following. This line segment between the centers we can definitely find because it's unique. We know what the centers are. They're not changing. The points here, these are going to be the closest possible points. That's the idea. Now, you might say, well, a picture seems pretty convincing, but how do I know that's true? So I'm going to do a little bit of a what's called hand waving here, but I think that you'll agree with me with a couple of basic ideas, and assuming you agree with me on the basic ideas, then everything else works out. So here we go. First idea number 1, and I'm going to say it out loud. If I want to go as quickly as possible, in other words, the shortest distance between a pair of 2 points, I should always go in a straight line. Yes? Okay. Good. That's all I need. Now, suppose I were to look at any other 2 points. So suppose I look here, say between that point, and I want to ask the question, is this line segment here longer or shorter than that line segment there? Well, now what we'll do is we'll actually produce this little path here. So what can I do? I'm going to go from the center out to my first point, across to the other point, and then to the other center. And I'm going to compare it to my original drawing here. So what's true? Well, if you look, it's fastest to go in the straight line. So this is the shortest possible route. Now, let's compare the two. Here, if I look, I say, look, the difference between these 2 paths corresponds to the lengths here, because these are equal, they're radii, they match. These parts are equal, the radii of the other circle, they match. So the only distinction is these parts here. And therefore, it has to be the case, since we know the shortest route is the direct route, that this segment is shorter than that segment. Okay, good. By the way, the idea that says, hey, the fastest way to get between 2 points is to go in a straight line It's sometimes referred to as the triangle inequality. We'll see it again later on. But just remember, if I want to go as fast as possible between 2 points, go on a straight line. So how does that help us answer our problem? Well, now we say, look, I don't have to do any geometry at all because I say, if I know those points, I'm good. That's the closest possible. Now you might say, well, that sounds hard. Do we have to find those points? And the answer to that is, no, we don't even have to do that, right? Because what are we after? We're not actually after the points which are closest. Our answer should be a distance. So our great aha is to say, if I know the distance from the centers, I'm almost to the minimum distance. What am I off by? I'm off by these radii. And so that's my amount off. So I can say idea. And here we go. So min distance is equal to distance from centers minus the radii. That's it. Okay, so that's how we go. All right. So now back to 3 dimensions. Okay, so what do we do there? Same philosophy. I say, look, what I'll do is I'll think of the straight line connecting them. So I want to find the distance between the centers, and then I want to subtract off the radiuses. Do we know what the radiuses are? Well, we can see, right? 4 and 9, 2 squared, 3 squared. So you can see, well, look, that has radius 2, that has radius 3. Okay, now what? We need to also identify the centers. So for the one with radius 2, the center would be at 1, 0, 2. For with radius 3, the center here is at -2, 5, -2. Okay, so our distance to centers, our distance from centers, would be the square root of, take -2, subtract -1, so that's -2 minus 1 squared, plus 5 minus 0 squared, plus -2 minus 2 squared. So that's the square root of, that's -3 squared, 9, 5 squared, 25, and let's see, 4 squared, and 16 years ago, what? No, wait, that's not it. 16, 4 squared. Okay, so what do we have? Well, 9 plus 25 plus 16 is square root of 50. And well, you can factor out 25 times 2, so this is the same as 5 root 2. Now, remember, that's the distance from the centers. We want the closest between the spheres, so we need to also subtract off the radii. Radii are 2 and 3, so 2 and 3 makes 5, and therefore our final answer, well, it's 5 root 2, subtract 2, subtract 3, or 5 root 2 minus 5. And there we go. Now, we should actually check one small thing, because there's a possibility that what if the spheres were actually drawn not like this? What if they had been drawn something where they overlap? And then what would happen? Well, then the nearest distance would be 0. How would we check to see that? Well, what we would look at is say, let's look at the value of this. If they actually overlapped, what would end up happening is we'd end up with a negative value at the end. So the question is 5 root 2 minus 5 positive or negative? And good news, it's positive. All right, and therefore we had the right picture in mind. But remember, you should always stop at the end and ask, hold on, is this answer reasonable? Because if the answer to that question is no, something interesting has happened. And, well, that means we should go back and think about what our situation is and do more work. Okay, so I guess I should write down so we don't forget, and our basic key geometrical insight is it's always fastest to go in a straight line. That's our key idea. It's a nice way to start building up our geometrical intuition. Okay, good. Well, let's do another problem. And this will be our last problem for now. But here we go. Use the distance formula to find an equation corresponding to the points x, y, z, which are equidistant, i.e. have the same distance. In fact, we can see the word equidistant means same distance because distant, well, that's distance, and equa is equal. All right, from -2, 1, 4, and 6, 3, -2. Simplify as much as possible. Now, when we talk about an equation, we're really talking about some expression that involves an equality and has x, y, and z involved in some way, shape, or form. We don't know how yet, but we need to figure that out. That's our job. Now, simplify as much as possible, that's an interesting, highly ambiguous phrase. Usually it just says, try to make it look nice. And so that's our goal, is we're going to say, let's try to make things look nice. Now, the good thing about this problem is it kind of tells us how to start. Even though it doesn't feel that way, we can say, hey, we know things have to be equal distance. So this is about starting with distance formulas and saying distance formulas which are equal to each other. So we say, okay, so we're going to write down our two different distances. So let's start by saying, let's look at the distance from x, y, z to -2, 1, 4. So that would be x subtract -2, which is x plus 2 squared, plus y subtract 1 squared, plus z subtract 4 squared, and then we would take the square root of that. All right, so that's the distance from x, y, z. That, by the way, looks dangerously like I just emphasize, that is a 4, to the first point, -2, 1, 4. Now, the next thing is we write down the distance to the other point. Okay, well, that would be x subtract 6 squared plus y subtract 3 squared plus z subtract -2, which becomes z plus 2 squared. And we take the square root of that. So those are the two formulas for distance. We know they need to be equal. So the last thing to do is equal. Okay, now we say, aha, we've taken the word equidistant and said this is what it translates into. There we go. What do we do now? Well, the rest of it is simplify as much as possible. In essence, we have an equation. It doesn't seem very simple. So let's start thinking about things that we can do to make this look nicer. Because we want things to be nice. That's sort of a common theme in math, is to say, hey, let's take things that don't look nice and simplify, simplify, simplify. And if we simplify enough, they become nice. All right, so what can we do? Well, I don't like the square root. Easy fix. If we square both sides, then we get rid of the square roots. So, good. And you might say, are you allowed to square both sides? Yeah, absolutely. If you square, as long as you do the same operation to both sides, you have to be equal. So we say, all right, x plus 2 squared plus y minus 1 squared plus z minus 4 squared is equal to x minus 6 squared plus y minus 3 squared plus z plus 2 squared. All right. Now what? Well, I see a lot of squares. Time to expand. Okay, here we go. Lots of practice expanding things. X plus 2 quantity squared would give us x squared plus 4x plus 4. Y minus 1 quantity squared, y squared minus 2y plus 1. Z minus 4 squared, z squared minus 8z plus 16 equals, keep going, x minus 6 squared, x squared, minus 12x, plus 36. Y minus 3 squared, y squared, minus 6y, plus 9. Z plus 2 squared, z squared, plus 4z, plus 4. Now at this point, you're probably thinking, I don't know if this is simplifying. It seems to be getting longer. But you know, sometimes things have to get a little bit longer before they compress again. Because what we're doing is trying to say, let's try to set things up for cancellation. Now, take a look. Does anything cancel? Yeah. In fact, some really great things cancel. The x squareds, the y squareds, and the z squareds. All the things that were squared are gone. Amazing. Amazing. Okay, what's the other thing to do? Well, now nothing else is really canceling, but we can start grouping. So let's put all the variables on one side and all the constants on another side. Okay, so what would that do? Well, I'd move the minus 12x across. So let's see, 4x plus, because if to move the minus 12x, it would become a plus 12x. So that'd be 16x. Minus 6y would come across as a plus 4y. Sorry, a plus 6y. And then there's minus 2y would be a plus 4y. Here, there's a plus 4z, come as a minus 4z. So that's minus 12z. Okay, so I'm just going to mark what we've grabbed. We've grabbed the x, the y, and the z terms. Okay, so that's what we have. Now, equals, well, let's add these up. 4 plus 1 plus 16 is 21. And that's going to move across as minus 21. 36 plus 9 plus 4 would be plus 49. All right, good. Well, 49 subtract 21 leaves us with 28. Well, almost there. It looks like, can we do anything else? Well, all these numbers, 16, 4, 12, 28, they're all multiples of 4. Well, let's divide by 4. 4x plus y minus 3z equals 7. Wow, that looks really simple. In fact, a lot simpler than what we started with. It's almost as if there's something going on here. Well, that's because there's something going on here. Now, you might start to wonder, hey, is there a faster way to do this or a different way to do this? And the answer is, oh, there's a beautiful way to do this. We're going to do this problem again in a few more sessions in a completely different way, where what we'll do is we'll use a little bit more geometry. And geometry is really powerful, but you have to build up that geometrical intuition, which is what we're working on right now. But that's it for this session of practice. Thanks for coming, and keep doing more practice on your own. And the more you do, the better you'll be. All right, have a great day.